Hello, let's talk about sequences. We're going to talk about the definition of a sequence, and we're going to get into some examples and write out some sequences, and finally talk about convergence and divergence of sequences. So to start off, the definition of a sequence is a list of numbers written in a definite order. This is our sequence notation for a sub n. So this first number here, a sub 1, we can go ahead and call that the first term. This second number here, a sub 2, we're going to call that the second term, and so on. And typically we're going to just call this the nth term. And you'll notice we have a dot 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 at the end here because this sequence that we're going to deal with, they don't really end. We're going to deal exclusively with infinite sequences. And infinite sequences basically mean that the sequence isn't going to have like a final number here. It's just going to keep going on and on. Another way to say that would be that each term a sub n will have a successor a sub n plus 1. So this basically covers the definition of a sequence, but now let's get into some actual sequences and explain them and write some out. We'll go ahead and have our defining formula over here, and then over here we'll write out the terms in the formula. So let's start off with a really simple one. Let's start off with a sub n equals n over n plus 1. I'll go ahead and do first several terms of the sequence over here. So a sub 1, we're just going to simply plug in this 1 for the n value up here. So it's just going to be 1 over 1 plus 1. So that's just going to be 1 half. A sub 2, we're just going to plug in this 2 for n. So it's just going to be 2 over 2 plus 1, which is just going to be 2/3. So let's go ahead and plug that in up here for our second term. Third term, similarly, it's just going to be 3 over 3 plus 1, which is going to be 3/4. You're probably getting the hang of this now. Our fourth term is just going to be 4 over 4 plus 1, or 4/5. And in general, our nth term is just going to be n over n plus 1, as we defined here. So let's go ahead and move on to another one. A sub n equals square root of quantity n minus 3, where n is greater than or equal to 3. So notice that n doesn't always have to start at 1. Like we did in this case. Typically it starts at 1 unless you say otherwise. In this case we're saying n is greater than or equal to 3. You'll notice that if we started at anything less than 3, we're going to get the square root of a negative number, which we can't do unless we introduce imaginary numbers, which we're not going to do here. So our first number here in this sequence is going to be a sub 3, and that's just going to be the square root of 3 minus 3 equals 0. I'll go ahead and plug that in for our first term up here. Next term is just going to be a sub 4, so that's just going to be the square root of 4 minus 3, which is going to be square root of 1, which is going to equal 1. So go ahead and plug that in for our second number. And a sub 5, square root of 5 minus 3 equals square root of 2, and you can kind of see where this is headed now. It's going up here. So let's just go ahead and fill in the next one. It's going to be square root of 3. Big surprise there. And if we keep on going, whatever n is, we just plug that in. That gives us our nth term, square root of n minus 3. So moving on, we've got one more sequence example, and this is going to be defined a little bit differently. It's going to be defined as a recursive sequence. And in this case, we're just going to define our first term, then we're going to define the subsequent terms in connection to the previous term. So this is what it looked like. We're just given our first term here, a1 equals 3, so we can easily just pop that one over here, first term. Our second term, we can call it a sub 1 plus 1, which would be a sub 2. So a sub 2 is just going to be the previous term, a sub 1 plus 2, which is going to equal 3 plus 2, which equals 5, which we can go ahead and plug in here for our next term. And our term after that, a sub 3, is going to be the previous term, a sub 2 plus 2, which is going to be 5 plus 2, which is 7, which we can plug in up here. And if we keep going, you can see the pattern here is pretty obvious. We're just going to add 2 each time, so the next term is going to be 9, etc. So this covers some of the basic types of sequences that you might run into. But one more thing we're going to discuss in this video is convergence and divergence. So let's go ahead and define what we mean by that. Convergence of a sequence. If the limit of our sequence a sub n as n approaches infinity exists, then the sequence converges. Conversely, if the limit of our sequence as n approaches infinity does not exist, then the sequence diverges. So this is the basic idea, basic definition of it, but it might help to just kind of go through the examples we just went through and see whether they converge or diverge, and go ahead and apply this criteria here. Find that limit of a sub n as n approaches infinity. So going back to that first formula we had here, that simple one, we can go ahead and take the limit of this sequence as n approaches infinity. So we just take this here and we just plug it in for that a sub n. So plugging that in, we end up with this limit here. And what we can do is just multiply the top and the bottom by 1 over n. And if we do that, we get n over n on the top and n over n plus 1 over n on the bottom, and we can just go ahead and apply that limit here as n approaches infinity. Well, it doesn't matter, this is just going to go to 1 because these terms are the same, and this 1 over n is just going to go to 0. So we're just going to end up with 1 over 1. So this limit is going to equal 1, and since that limit equals 1, we know that limit exists because it comes out to be this number, and so since that limit exists, we can say that the sequence converges. And maybe it may help to show this graphically as well, so let's do that. Let's get rid of all this stuff here and just put this graph up. So if we plotted these out, we're just going to get some points for these different terms in the sequence. So our first one, this is a sub 1, so we're going to go for our 1 value here. It's going to be at a half. And for n equals 2, this is going to be about 2/3. For n equals 3, 3/4. For n equals 4, well, that one's easy. It's going to be right there. So you can see these are getting bigger and bigger, but they're getting bigger slowly. And as we showed before, this limit's going to be right here at 1. And so graphically what that means is these numbers will keep getting bigger in the sequence, but they're never going to go past 1 here. This is going to be sort of an upper limit that they're not going to pass. So what that means is when n gets really, really big, the numbers will get bigger, but they're never going to pass 1. So that means this sequence is going to converge. And so now let's look at what happens to that next sequence that we looked at. So this is our next sequence. And we can go ahead and apply that same limit. And we can go ahead and find that same limit of a sub n as n approaches infinity. And again, we're just going to sub this right here in for a sub n. Doing that, we end up with this, and I just made it to the 1/2 to make this a little easier, because what we can do with this is apply one of the limit laws that says that we can just sort of take this limit here, find this limit, and take it to the 1/2 power, and it's actually going to work. The limit laws allow us to sort of put those parentheses there. So doing that, we end up with this equation, and now you can see this is pretty clear. As n is approaching infinity, well, this limit here is going to approach infinity as well. And then we just have that to the 1/2, which is still going to be infinity, which just means that this is going to increase without bound. We can make this square root of n minus 3 as big as we want if we make n bigger and bigger. Since this limit equals infinity, it does not exist. So the sequence will diverge. And again, if we want to look at this graphically, we can see that if we plot out each of these numbers here, bring them down to this graph, we end up with these dots here. And you may say, well, it looks like it might kind of plateau here at 2. But if we kept going out, we see it doesn't. It'll go past 2. And then it'll go past 3. It'll go past 4. It can go past any number that we pick. This value can go as high as we want in the y direction by making it a number as big as we want in this n direction here. Therefore, we can see graphically also that this sequence is going to increase without bound, and therefore it's going to diverge. So, in summary, we looked at several different sequences. We looked at the definition of a sequence and how to write them out, and we found that this first series converges. We found that this second series diverges. So that concludes our introduction of sequences, and the next thing we'll discuss are series, which is basically just the sum of the terms in a sequence.